Good afternoon, class. We are looking at exam 1 review, limits covering from 1.6 to 3.1, 1.6 to 1, 2.1 to 2.5, and 3.1. We are going to look at questions that mostly you've seen in your lectures, okay? And some of them from the exam review that is posted under the modules of Canvas. This is one example is from there. So we want to find the general term for the sequence. And as you know, finding the general term sometimes is very complicated. You notice this as, difficult as it gets. You notice there are three things. The sign changes, and you have the numerators, you have the denominators. So you look at three things. The sign. Because it alternates, you use one of these two. So we are going to write a sub n when we are done. The sign, numerator over the denominator, and the sign alternates. So it's either -1 to the power of n or -1 to the power of n minus 1. The question is which one? Well, just plug in 1. If you plug in 1 here, you get -1. If you plug in 1 here, you get -1 to the power of 0, which is +1. And look at this one. The first one is positive, so clearly we must choose this one. Let's write the numerators. We are adding a constant 4. That's an arithmetic sequence. The first term, a sub 1, is 6, and the distance or the difference is fixed at number 4, which means we can use the general term a sub n equals a sub 1 plus n minus 1 times d. A sub 1 is replaced by 6, and d is 4. This is 4n minus 4. We combine the two numbers. The final answer is 4n plus 2. We write the denominators, and we notice if we multiply by 3, we get the next term. That means we are dealing with the geometric sequence such that the first term, a sub 1, is 3, and so is r. We use the general format. A sub n is a sub 1 r to the power of n minus 1, and a sub 1 is 3, and notice the exponent is 1 when we don't write it. And following this method, you add up the exponents and you get 3 to the power of n. And now we are going to follow this, and we say a sub n is this piece, -1 to the power of n minus 1. Then fraction bar, the numerator is this piece, 4n plus 2, and the denominator is 3 to the power of n. Are we done? No. Make sure you check. So if I put n equals 1, -1 to the power of 0 becomes +1. This becomes 4 times 1 plus 2, 6 over 3 to the power of 1, 6/3. You really should check a couple more to be on the safe side. So you check your work. Always check your work. General term is given. We want to find the first 5 terms. This was done in class, so quickly we're going to go over that. Just plug in n equals 1. You get 2 to the power of 1 minus 4, which is -2. If I replace the n with 2, 2 squared minus 4 is 0. If I replace it with 3, I get 2 cubed. 8 minus 4 is 4. And we can figure out the rest. Example 4, find the first 6 terms of the recursive sequence. A sub 1 is 1, A sub 2 is 2, and A sub n plus 2 is A sub n plus 1 plus 2A sub n, which means if you're looking for a term, pick the one before that, and then plus 2 times the one before that. So if I want A sub 3, if I want this one to be 3, that means 2, that means 1. So I have A sub 3 is A sub 2 plus 2 times A sub. A sub 2 is 2. 2 times 1 is 2, they add up to 4. If I want the next one, if this is 4, that means 4, 3, 2. A sub 4 is A sub 3 plus 2A sub 2. So 4 plus 2 times 2, they add up to 8. So if I want A sub 5, everybody, so if I want A sub 5, so I want the previous one, A sub 4, plus 2, the one before that, A sub 3, which means I want 8, and then 2 times A sub 3, 2 times 4, 8, and 8 is 16. So A sub 5 is 16, and you can figure out the rest. Limits of a sequence, example 1, finding sequential limits, the limit of 2 to the power 1 as n approaches infinity. So we are going to remember the theorems that we observed. The limit of r to the power 1 as n approaches infinity. It depends on the value of the base r. If it's between -1 and 1 is 0. If it's 1, it's 1. And if it's larger than 1, it's infinity. So in this case, is larger than 1. So 2 to the power of infinity, remember, we simply plug in. So 2 to the power of infinity, and we get infinity, which diverges. We do the same thing here. We plug in. 2 to the power of negative infinity, it follows the negative exponential. So it's 1 over a to the power of m, meaning this, everybody, is 1 over 2 to the power of infinity, which makes it 1 over infinity, which makes it 0, 5. It's convergent, so it converges to 5. Again, we plug in and remember this theorem, which simply indicates the limit of 1 over n to the power of the p as n approaches infinity is 0 for p being positive. In this case, p is 1. P is 1. So you get 1 plus 0 or 1, which is, again, convergent. So it converges to. What about this limit? You are dealing with a rational expression. A rational expression. N is approaching infinity. And by the way, if you plug in, you get infinity over infinity. The technique is to divide by highest degree term in the denominator. We get this one. Each one of these goes to 0. 3 over n means 3 over infinity is 0. Minus 1 over n squared, that means minus 1 over infinity squared. Each one is 0. So you get 2 over 5 as the final answer. All right, again, this comes from the lecture 0.46 bar. We want to write it as a rational number using geometric sequences and series. There are actually different methodologies. For example, in algebra, you may set this equal to x and solve it. So it's equal to 0.464646, and it continues indefinitely. This part is 46 over 100, or 0.46. This part is 0.0046, or 46 over 100 squared. And this part is 46 over 100 cubed, or 0.000046. So whether you go with the rational format, fractional format, or decimal format makes no difference. Needless to say, we can simplify this, but on purpose, I like to keep it intact because I want you to know where the numbers are coming from. And this is a geometric sequence with the first term being 46 over 100, or 0.46. What is R? Since this number is 100 times larger than this, the fraction is 100 times smaller. It makes R between -1 and 1. It's 1 over 100, or 0.01. Therefore, A over 1 minus R can be used. And we are going to do that. Now, you can use fractional format or decimal form. If you go with the fraction, you're dealing with a complex fraction. You will multiply the top and the bottom by LCD, namely 100, to fix the problem. This becomes 46. This becomes 100 minus 1, or 99. This can't be simplified, and you're done. If you want to go with the decimals, so you write this one and this one. The numerator is 0.46, and the denominator is 0.99. And I hope you see that these two are the same. This is a question from the exam review, and the difference is that the repeating decimal is just one of those decimals. Therefore, this means 3.1666. That's the only number that repeats. Number 1 does not repeat. So it's 3.1 plus this part. And please understand, for example, this is 0.06, or 6 over 100. This is 0.006, or 6 over 1000, and so on. So this part is the repeating part, either in the form of a fraction or decimal, makes no difference. And this is the part that follows a geometric series. So what is the first term? This one. And you're going to write both fractional and decimal format. Now, please notice this is 10 times larger than this, because this is 1000. So that means the fraction is 10 times smaller. So R is 1 over 10, or 0.1, 0.1. And again, we can use this because R is between -1 and 1. So for this part, so this would be 3.1 plus this part, and this part uses the geometric series, either the fraction or decimal format. If you go with the fraction, the first one again, 6 over 100 class, we know it can be simplified. I don't want to do that on purpose, again, because I want everybody to see where the numbers are coming from. Or you can put the decimal. So if you go with the fraction, what do you get? Well, first you have to simplify this complex fraction. You multiply by 100, the top and the bottom. So just sticking with that, when you multiply these two, you get 6. When you multiply these two, you get 100 minus 10. So this part is 6 over 90. And I want to go back to the decimal. If I dealt with the decimals, this one means this number at top, and this one means 0.9 at the bottom. And I hope you see, if you multiply the top and the bottom by 100, you get the same number. Now, as you know, 6 over 90 is 2 over 30 and 0.1. So this, because we want to write it as a rational, as a fractional format. 0.1 is 1 over 10, okay? And 6 over 90 is 2 over 30. And to combine these two, this is the same as 3 over 30 because 30 is the common denominator. So 3 and 2 is 5 over 30. And 5 over 30 is 1 over 6. So 3 and 1/6 is the final answer. And this is as complicated as it gets when you have a repeating decimal, but the repeating part is not all decimals, it's some of it. A doctor prescribes a 100 milligram antibiotic tablet to be taken every 8 hours. Just before each tablet is taken, 30% of the drug present in the preceding time step remains in the body. How much drug is left after the third tablet? Write the expression for Q sub n plus 1 in terms of Q sub n, and so on. We want to write the given first to understand it follows the formula that is used for patients, and we have to write the given first. To write the given, we notice that this is using Q instead of B. We're going to change everything to Q, so we're going to write the given first. Q sub 0, it is mentioned here that is 0. Q sub 0 or B sub 0 is always 0. In this case, we're going to use Q instead of B. So Q sub 0 equals A equals 0. The lowercase c is fixed at 100 milligrams and R is 30% or 0.3. So to make up a table, the first one is 100. And the second one, 30% of that is 30 and 100. It's 130. Now the next one, 30% of 130 is 39. Add 100, we get 139. That's how we come up with those. Write the expression for Q sub n plus 1 in terms of Q sub n. That means go to this formula and change the B to Q. So B sub n plus 1 is R B sub n plus C. And we are going to say Q sub n plus 1 is R Q sub n plus C. And then just use the given. That's why it's important to write the given. We are going to change the R to 0.3 and lowercase t C to 100. By the way, the 8 hours is a time step, which is extremely important, but it doesn't enter any of the formulas. We want to solve for Q sub n. That means use this formula and change the B to Q. So the same formula is used, but B is changed to Q. And now use the given. Of course, Q sub 0 is 0, R is 0.3, and lowercase c is 100. Plug in. And now we are going to simplify. To do that, this is 0. This is 0.7. Put it underneath 100. We get 100 over 0.7 times 1 minus 0.3 to the power of n, and this is 1,000 over 7 because we don't want to have a decimal in the denominator. It says use part C to find Q sub 3. In this formula, n equals 1 gives you the first one, 2 gives you the second one, 3 gives you the third one, and I highly recommend you try it. For example, 1 is easy to see, becomes 1 minus 0.3, which is 0.7, divided by 7 is 0.1 times 1,000 gives you 100, and you can try the other ones. What's the limit? Let's take the limit. When you take the limit and use the limit laws, you bring this number out and you take the limit of each piece. The first one is a constant. That gives you 1. And this one, because the number 0.2 is between -1 and 1, that goes to 0. We get 1,000 over 7, which is 142.857 milligrams. What does this mean? If this, let me erase this. If this antibiotic is taken every 8 hours, it will never get beyond this much, 142.857 milligrams, that they have found it to be safe for the patient. That's the idea. We want to find the limit of the function at infinity. First, reminding you to find the limit, just plug in and observe. It gives you a number, you're done. 0 over a number, of course, other than 0 is 0. A number over 0 tends either infinity or negative infinity. But in calculus, most of the time we deal with indeterminate forms of 0 over 0, infinity over infinity, infinity minus infinity, and so forth. In this case, it's infinity over infinity. The technique is, because this is a rational function, and the t, the variable, whatever it might be, is approaching infinity, you divide by highest degree term in the denominator, namely t squared in this case. And you simplify. And this is what you get. Because this one, the denominator is t or t squared, each one goes to 0. So the numerator is 0, the bottom is 1, and you end up with 0. What happens in this case, similar to the previous one, you are dealing with a rational expression. T is approaching infinity. You divide by highest degree term in the denominator, because no matter what, if you plug in, you get infinity over infinity. And again, you simplify. These two pieces, of course, they go to 0 because t approaches infinity. The numerator is infinity plus 2, or plus any number is infinity. Divided by 5 or 5,000, it is still infinity. And that's the final answer. The limit of the square root of x squared plus 1 minus x, if you plug in, you get infinity minus infinity. And the technique is to multiply by the conjugate, reminding you that the conjugate of a minus b is a plus b, which gives us a squared minus b squared. So the conjugate of this expression is the same thing with the plus x instead of minus x. You put that in the top and the bottom as well. And the numerator, you can extend this fraction bar. And the numerator, when you multiply these two, you get square root of x squared plus 1 quantity squared minus x squared. And the first piece comes out. This is what you get. And you can drop the x squared and negative x squared. And now if you plug in, the denominator has infinity and infinity, or two infinities, if you will, and any number divided by infinity is 0. So it's easy to see that. Now what happens? Again, you just plug in everybody. And e to the power minus t is 0 because we use the negative exponentials. E to the power minus t is 1 over e to the power of t, which means 1 over e to the power of infinity, which means 0. And so the answer is 12 over 4 or 3. In this case, if you plug in, the numerator becomes infinity, the denominator becomes negative infinity class. This is not a rational expression, but we treat it as one because it's a fractional expression. Since t is approaching infinity, we divide by highest value. We can't say highest degree, highest value in the denominator, which is e to the power of t, and we simplify everybody. Of course, each one of this goes to 0, and you get positive 1 over negative 3, which is negative 1/3. Now, the limit of x squared minus x as x approaches infinity, you plug in, you get infinity minus infinity, and the technique is factoring. When you factor, you get the limit of x times x minus 1 as x approaches infinity, which is infinity times infinity minus 1, and the result is still infinity. Okay? This one, if you plug in, you get infinity over minus infinity. You're dealing with a rational expression. X is approaching infinity. You divide by highest degree term in the denominator, namely x. So you divide everything by that. Now you plug in. When you do that, the numerator is infinity, everybody. Denominator is a negative number, so that's why it changes the sign to negative infinity. And that's what I mean. You want to be very careful when you deal with a case like that. So you're dividing by a negative number. Positive over negative is negative, everybody. All right. Given the graph of a function, state the values if they exist of the following. So we want to find the limit, and reminding everyone about the one-sided limit, which means the limit of f of x as x approaches a equals L if one-sided limits are identical. Because we want to find the limit of g of x as x approaches 2, we look at one-sided limits. That means we're going to look at 2 from the left, this way, going this way, moving towards this point, having the y coordinate 3. From the right, going this way, the right of 2, you're in this branch of the function, moving towards this point, which has the y coordinate 1. Are these two the same? No. The limit of g of x as x approaches 2, dne does not exist. We are going to look at the same thing for number 5, the limit of g of x as x approaches 5. And again, because we are interested in phi, we are going to look at the one-sided limits, the limit of g of x as x approaches 5 from the left, meaning this way, meaning going this way. And if we approach 5 from the right, meaning going this way. And in both cases, left or right makes no difference. We're moving towards the same hole, which has a y coordinate 2. So the left one gives us 2. The right one gives us 2. Because the two are identical, the limit does exist. However, you have a solid point. What does it mean? That means the functional value precisely at 5 is 1.4. So g of a 5 is roughly about 1.4 because it may be slightly different, which is not equal to the limit, which is 2. And that gives you the fact that it's not continuous. I'll remind you, the definition of a continuity is that the limit of f of x as x approaches a equals f of a. If these two were the same, then the function would be continuous. The function is discontinuous at 5, also at 2. However, 5, you have only one problem. The functional value is different. So we can fix it. This is called removable discontinuity. G of x can be CTS, short for continuous, at x equals 5 if we redefine the functional value g of 5 to be 2. In other words, if we move this and make it here, that's all. But what happens at 2, this is also discontinuity, but there's nothing you can do to fix it because it's a jump. So the main problem is that it's a jump. Of course, g of 2, we don't have a solid point. We don't know what's g of 2 either, but that doesn't change the fact that it's a jump and it can't be fixed. So when the limit exists, we can fix the discontinuity. When the limit doesn't exist, we can't. We cannot. Okay. Reminding you of a VA, vertical asymptotes, have an equation of x equals a if the following definitions work. The limit of f of x as x approaches a, or a from the left, or a from the right is positive or negative, infinity. In those cases, we say the vertical asymptote has the equation x equals a. So we want to look at number 2. And notice from the left of number 2 or from the right of number 2, either way it's going down towards negative infinity. For number 5, from the left of number 5 or from the right of number 5 makes no difference. It's moving up towards infinity. Now, negative 3, it depends. You're approaching it from the left or right. So from the left, of negative 3, as we approach negative 3 from the left, it goes down to negative infinity. But from the right of negative 3, it moves up to positive infinity. And so those are the vertical asymptotes. X equals 2, x equals 5, x equals negative 3. This one says x equals negative 3. This one also says x equals negative 3. Those are the vertical asymptotes. And here's the equations.